All right, well, thank you very much for this warm welcome here at the KIT Climate and Environmental Center. It's a great pleasure to be here. So I hope in the next 45 to 50 minutes I can share with you a few thoughts about climate change and something that concerns me personally as well since a few years. The question, what happens if Paris fails? Or perhaps the question before, can Paris fail? We'll see. Now, we're all basically in climate change research when it comes to asking about anthropogenic climate change and its impact on people and on other systems on this planet, guided by this Article 2 of the United Nations Framework Convention on Climate Change, which says that the ultimate objective of this convention is to stabilize greenhouse gas concentrations in the atmosphere at a level that prevents dangerous interference with the climate system. This is really a fundamental article that is in this convention that is in force since March 1994. It's quite a long time ago. And until December 2015, it wasn't really clear what we regard as dangerous interference. And so I'd like to recall this historic moment of 12 December 2015, when the Paris Agreement finally was concluded in consensus by 195 countries. That was in 2015. Two countries were not present at that time. It was Nicaragua, for reasons not really known, and Syria. Nicaragua has joined in the meantime, but another larger country has announced that they will withdraw from the Paris Agreement. Now, in the Paris Agreement, we have three key statements that are the cornerstones of the Paris Agreement. The first is that efforts should be made that the temperature increase relative to pre-industrial stays well below 2 degrees Celsius. And note the well below. That's in this article in there, and it often gets forgotten when we talk about the 2-degree target of Paris. The second one, equally important, and the reason why actually a large number of countries, in particular in the Pacific region, have joined in consensus, is this more ambitious target of 1.5 degrees Celsius above pre-industrial levels. And finally, a sentence that comes out of decades of research and is no longer questioned is this one: to achieve a balance between anthropogenic emissions by sources and removals by sink of greenhouse gases in the second half of this century. Of course, you realize that these are politicians' crafted sentences. A balance between sources and removals by sinks. It wasn't possible to say emissions should go to zero, so they wanted to have the possibility in there that emissions continue, but they are compensated by sinks. All right, the scientific basis of this historic achievement of the Paris Agreement was really laid even before the legendary Earth Summit in Rio that took place in 1992. The Intergovernmental Panel on Climate Change was founded in 1988, and just 2 years after the first assessment report came out, and I remember still when I was a postdoc, I was reading in awe this thick report that combined essentially the world's knowledge, scientific knowledge about anthropogenic and climate change in general. I was very impressed. I still remember one of the lead authors came by our institute in Canada and lamented about the humongous task that was before him to complete this chapter in time. So very similar effects happened for every of these 5 reports. You see that these reports appear in a frequency of about every 5 years. The last one, 2013, and as you also are aware, the 6th assessment report is well underway. On October 8, the first installment of the 6th assessment report in the form of a special report will be announced to the public. Just to give you a little impression what that means, I co-chaired, as was mentioned already, Working Group 1 during 7 years, together with my colleague from China. If you carefully look at this picture, I lost a lot of weight during this process, in particular in the 4 days in which we negotiated the summary for policymakers. This is a summary of 27 pages. Every single word, every figure, every detail is basically open to negotiation. And any country can raise their hands and say, oh, maybe we're not quite sure whether this is a robust result. Could you not please reformulate that? And so you have to negotiate, you have to revise until consensus is established. And to lead this process cost me quite a few kilograms in these 4 days and a couple of nights, of course. But then on September 27th, 2013, we had a few really tangible statements in our summary for policymakers, which, as it is customary for United Nations documents, were accepted in consensus. And I show you some of those. Warming of the climate system is unequivocal. That may sound trivial to you, but in 2013, we were in a special circumstance where media and other interested circles made a lot of noise about the so-called climate pause, the fact that the global mean temperatures haven't risen as steadily as they did in the last 60 years for the last 13 years. And that was pounded over and over again to the extent that at the press conference I had again to respond to this question, which we did address indeed in the summary for policymakers. So it was important to reiterate that statement that was already there in the 2007 4th assessment report. Warming of the climate system is unequivocal, a consensus statement that you find in the summary for policymakers. This one was seemingly more difficult. The scientists who drafted the summary for policymakers proposed this sentence: human influence on the climate system is clear, full stop. And this sentence was among ourselves with the scientists. People said, well, you will lose the sentence. Don't even try. This is too clear, too simple, and too provocative in a way in a circle where some of the countries actually say, well, we're not quite sure whether climate change is actually caused by human activity. And so we took a stride and said, okay, we'll propose that sentence to the policymakers and the delegates. And in fact, given the evidence that was in the area of detection and attribution of climate change, a science direction that has started around 2001 with some key papers and has evolved ever since into a mature subtopic in climate change science, delivered so many results that the policymakers and the delegates, in fact, accepted that sentence only after 20 seconds of my announcement. This is the sentence. Please raise your hands if you would like to comment on that or propose revisions. Nobody raised their hands, and I could gavel it down. This one is also an interesting sentence because it speaks directly to the Paris Agreement that was in the process of being prepared and developed in 2013, 2 years ahead of that conference. Limiting climate change requires substantial and sustained reductions of greenhouse gas emissions. Some people accused me of being an activist when we had that sentence passed and accepted. Well, they didn't take the English language too seriously. If you really read it out, limiting climate change is actually a conditional. If you want to limit climate change, then the following has to happen: a substantial and sustained reduction of greenhouse gas emissions. And again, that's a sentence in consensus. So Australia was in agreement, Saudi Arabia, Venezuela, the United States of America, all these countries unanimously said, yes, that is a valid statement out of the scientific assessment. And you can see that with this framework, in fact, the scientific basis was laid for an informed discussion and negotiation about the Paris Agreement. All right, so that's sort of the preface to the things that I would like to show to you tonight. This is certainly the most important photograph. It's almost 50 years old, in December 1968, taken by Apollo 8. For the first time, we see our home from a completely different perspective. From a perspective that shows how fragile our planet is, how habitable it is, and how such in a close-by location there is actually inhabitability, as you see with the surface of the moon. So habitability is something very special. Of course, you know why that is. I want to address 4 points tonight. Know the present, estimate the future. What do we lose if we fail in Paris? And the synergy of ambitions. This is, as you very well know, but I still show it in every lecture on climate change, the most important factual data that tells us something is changing, and something is changing fast and large. It is the concentration of the second most important greenhouse gas in the atmosphere after water vapor, carbon dioxide, that has been measured since 1958 in very high precision. And every month you can download the most up-to-date data delivered by NOAA. This delivery and this service has survived the new presidency of the United States of America. So regularly, every month, you still have these fantastic data. Of course, you may ask the question, well, has that concentration been at that high level already before in sort of human history? And this is a topic that we work on, have been working on for many decades at the University of Bern in my division. That is the analysis of polar ice cores. This is an ice core from Antarctica, from the EPICA project, the European project of ice coring in Antarctica. That ice contains air in the form of bubbles. The air, of course, is composed of the major gases, but also the trace gases, and in particular the greenhouse gases. So if we manage to date the bubbles based on the level of depth that these ice samples are coming from, and if we are able to analyze the composition of that air, then we're able to respond to that question. And here is the most up-to-date figure here over the last 800,000 years. And we can now affirm that, yes, indeed, in 2018, we are way off the concentrations that have been present in the atmosphere over the last 800,000 years. In fact, 30% higher than ever in the last 800,000 years. You see here the very nice sequence of the ice age cycles. About 8 ice ages have followed one another in the last 800,000 years, with the last glacial maximum where most of Switzerland was covered by ice about 20,000 years ago, a warm period around 130,000 years ago, and so on. So the chemical composition of the atmosphere has changed fundamentally, and the reason is also clear from many studies. That is also a scientific fact. This increase of carbon dioxide has been caused by the burning of fossil fuels, coal, gas, and oil, and deforestation, or more general land use. Other things have changed too, of course. The global mean temperature or the hemispheric mean temperatures, as you see them here in this graph, have increased by about 1 degree Celsius since the beginning of the 20th century. The climate pause, I can question you and quiz you, do you see a climate pause here? Of course, in 2013, when we had to deliver our assessment, it was kind of evident. But who has ever followed a course in primary school knows that in order to make a statement about climate and climate change, you have to measure at least for 30 years. Okay. And that was not the case in that media discussion. So the climate pause is not visible here. It was this little episode here. And sure enough, 2014 to 2017, every year in sequence has been a record year, with the exception of 2017, a little bit less. But these are the 4 warmest years since 1880 on a worldwide level. I've here a few slides from my colleague Christoph Scher from ETH Zurich, who has written in 2004 a very famous paper on the extreme summer 2003. And he has kind of followed that line right up to 2018, which was, again, a very extreme summer. As you can see here on this temperature scale for the summers, all summers that we have available measurements in Switzerland since 1864 get a tick mark here, a bar on this chart. And you see that the summers since 1991 have been exceptional. They all lie to the right side of this Gaussian distribution. And in fact, 2003, which was also an extreme summer in parts of Germany, in particular in France and in Switzerland, stands out really largely on this scale to the far right. 2015, 18, and 17, again, record summers. And just to give you an impression on the return periods that you would estimate from the Gaussian distribution, these have been truly exceptional summers on the order of exceeding 1,000-year return period if you assume, and this is of course not the correct assumption, I should stress, if you assume a random process. These times will actually change if you assume an autoregressive process or if you actually consider the linear or steady increase of temperatures since the beginning of the 20th century. In any case, we can extend this consideration to all the seasons, and this is even more impressive. You see again in red all those seasons that are following 1991. Again, for every season, the red bars are to the right of the distribution, and we can make a few statements about this graph. Several hot temperature records since 1991. You can read them off in every season. So it's not only summer that has become extreme, it's also the 3 other seasons. We have no cold temperature records anymore since 1991. Not a single red bar here on the left side of the distribution. There is one tiny one here, but nothing extreme. And we have extreme hot temperatures exceeding this 1,000-year threshold in all seasons. So for example, 2003 we've mentioned already, but in winter, 2007 in Switzerland was really warm. So this is a telling story about temperature, but also about the seasonality of the temperatures. And I think it's these observations that let us convince that really warming of the climate system is unequivocal. And if it's warming, then of course, other things have to change as well in a physical system. For example, sea level has to increase simply by the expansion of the water that is slowly warmed, but also, of course, because of the discharge of fresh water from the glaciers that melt from the ice sheets of Greenland and Antarctica. These are the latest measurements taken together since 1993, as you see here, from satellite missions. And I think something that we did not really put to the front line in the fifth assessment report in 2013 is the fact that the scientists are now more and more confident about, and that is the acceleration of sea level rise. You see here, this acceleration in this most recent study was actually quantified at definitely positive, at 0.08 millimeters per year. So in fact, this curvature of the mean curve here, this regression, is actually positive. Something that is of serious concern, of course. One contribution to sea level rise comes from the ice sheets I've already mentioned, from Greenland. And if you go to Greenland with the satellites above, you can now measure the movement of the ice on the surface. An incredible thing if you think about it, that we're able from satellite missions to quantify how fast the ice actually goes into the ocean. And there are a few outlet or hotspots in northern Greenland. Here I've indicated them. The fastest one is Jakobshavn, Isbry, with 13 kilometers per year of discharge. Of course, these outlet glaciers have always discharged ice to the ocean, but the question is, what is their temporal evolution of that discharge, and how does that compare to the overall mass balance? And the overall mass balance, we know that from GRACE, is actually negative. Greenland, as well as Antarctica, are on a serious diet. They lose mass every year, gain a little bit of mass in winter, but then they lose even more mass in summer. And here you see such a picture. If you fly along the terminus of Jakobshavn ice stream, the terminus is here, so you have a view into the ice sheet, that an increasing slope here. And just to give you a scale here, this iceberg that has just discharged from the ice body, that flank here is about 50 meters in height, which means that the iceberg goes down about 450 meters into the fjord. These are massive icebergs that are discharged into the fjord and then being emanated into Disko Bay and into the ocean. A number that you may wish to remember: Greenland today is losing about a cubic kilometer of ice. About a cubic kilometer of ice every day. And that cubic kilometer of ice, when it's melting, is contributing, among the other contributions, to the increase of sea level. Let's estimate the future. You're all familiar with this graph. I don't want to belabor that. It's the projection of global mean temperature based on two scenarios. The red one, a business as usual, and the blue one, the so-called RCP 2.6 scenario, which is more or less Paris compatible. So you see here for the 21st century an additional 1 degree warming. Add to that the 1 degree during the 20th century, and you are about at 2 degrees, whereas in business as usual, you will have about a warming of 5 degrees over pre-industrial. This, plus many other evidences from the climate model projections, led us to formulate in the synthesis report of the fifth assessment report the following affirmation: further warming will increase the likelihood of severe, pervasive, and irreversible impacts. It's quite a drastic and dramatic language, but again, the language that is supported by the scientific evidence and accepted by all in consensus. Of course, nobody lives in global mean temperatures, so you see here the regional distribution of the temperature. Again, a pattern, in fact, that we already observed today. more warming over land because of the reduced heat capacity, less warming over the oceans because of the absorption of heat into the ocean. And in order to close the budget, we're also able now to quantify the amount of heat that has already penetrated the ocean, in fact, worldwide, down to about 700 meters, and in the high latitudes down to about 2 kilometers. Here is a more recent result that has now turned the attention to basically the dominant surface of the planet, and that is the ocean. There have been years of studies about extreme events on land, all kinds of different types of extreme events, but extreme events in the ocean has come under the focus only very recently. Thomas Fröhlicher and Charlotte Laufkötter at our institute, they have looked at the occurrence of ocean heat waves. And you see, in the past few years, there have been a number of such heat waves already measured at the Earth's surface. But here is a more disturbing message, and that is the estimate how these extreme warm events will actually compare to the extreme warm events on land. This is just an analysis of the probability of the occurrence of warm events in a 2-degree world. And you see that, of course, there will be more heat waves on land. We can quantify that about a little bit less than doubling of that occurrence of heat waves on land. But in the ocean, you have a totally different situation. Since the ocean is a heat reservoir, the variability is actually subdued. That is why this distribution is not as wide as over the land. But any small change, and you see here this delta T is actually quite smaller than the delta T over land, which is compatible, of course, with the previous map. But even if that delta T at the ocean surface temperature is smaller, you see that the occurrence of extreme marine heat waves increases by a factor of over 8. So we are really looking at extreme or massive changes in the statistics of extreme events, also in the marine area, and there is still a lot of unknowns with regards to the impacts that such extreme events may have. Here is another graph of a recent paper by that colleague, and the question here is, what if Paris fails? So we compare here the impact of these marine heat waves in a metric of cumulative intensity. That's a metric that is measured in degrees Celsius times days, so the duration is an issue, and the intensity of the heat waves. And you see here on the horizontal the global warming, and on the vertical this metric. On this graph, different model simulations from CMIP-5 for the 2 scenarios, Paris compatible, if I may say, and business as usual, RCP 8.5. And by 2090, that is by the end of the 21st century, for Paris compatible, you're here at around 40 in this metric, whereas if you go business as usual, you're at around 240. So in other words, a factor of 6 increase in this impact-related marine heat wave metric, something extremely impressive, and it tells you just by this example how much is at stake if we fail to keep temperatures increase relative to pre-industrial well below 2 degrees Celsius. This slide should explain to you how urgent this problem is, how imminent the failure of the 2-degree target is. And that is probably the most important progress that we could report in the 5th assessment report. And I tell you, that concept took us 1.5 days to get accepted. there were some very fierce nations who opposed the concept of cumulative carbon and the concept that the sum of all emissions actually determines the warming in the 21st century. But in the end, science prevailed, and that is now figure 10 of the summary for policymakers. It tells you something about the carbon budget for any climate target. For the 2-degree target, that budget is plus or minus, with uncertainty of course, but about 800 billion tons of carbon. That's the amount that we can emit to the atmosphere so that the warming stays essentially below 2 degrees. Since, or up to 2017, we have used 575 billion tons of carbon through the burning of fossil fuels and land use change. That leaves us with 215 billion tons. You need to know how much we emit every year as a global community, about 10 billion tons of carbon. It's really simple calculations. And we can say under current emissions, and these emissions are still at that level of about 10 billion tons of carbon, under current emissions, the carbon budget will be consumed before 2040. And in plain language, that means we will have lost the Paris target, or Paris will have failed. This is a dramatic message. And I believe, and that's my opinion, that this message has not yet arrived with the policymakers in its really basic clarity. One sort of discusses all kinds of scenarios, but the fact that we are on the brink of losing targets, the first one will be the 1.5 degrees Celsius target, is something policymakers do not yet talk about. So what do we lose if Paris fails? Well, we need to recognize that climate change is a resource problem. And it was mentioned already in the introduction. I believe personally that this is the most important element of our public discussion regarding climate change today. It is not only about degrees Celsius and millimeters per year. The general public does not really like these physical units and has no relationship to them, but it's about resources, about the resources that are available to humans and the natural systems. And I want to just highlight 4 resources. The warming that we experience will affect the resource of health. We don't talk a lot about the resource of health, except when, for example, in Switzerland, every year the premiums for the health insurance increase steadily, almost as steady as the global mean temperature. Precipitation will change under global warming, and therefore the resource of water will be affected. We will see how. Sea level will increase under global warming, and that concerns the resource of land. Everybody who has looked at house or land prices know how precious land is to humans. And finally, the general climate change impacts, they will affect the resource of biodiversity. Something that is covered in a completely different UN convention that was also designed in 1992 at the Rio Summit, and which we only start to talk about very recently, about these interactions between climate change and biodiversity. Resource health, of course, it's evident to you that it's not very healthy to be close to this bushfire. These bushfires have increased in frequency and intensity, even to the extent that Sweden this year has experienced their first bushfires or forest fires. But what I want to draw your attention to is that there are also physiological limits of our body to the increase of temperature. And if it comes together with high levels of humidity, we don't really like that. In fact, we have the risk of heat collapses. And this study here has looked at a quantification of so-called deadly thresholds. That means a threshold where you would not survive if you did labor outside under such climatic conditions. And based on model simulations, they estimated the number of such risky days and the geographical extent. This is sort of the historical extent of these risky days. You see that India is quite affected by that, on the order of perhaps 50 days per year where it's not quite good to be outside and do hard labor. Other regions are also colored in yellow, but if you compare that to the distribution of that quantity in 2090 under a business as usual scenario, you see not only more intensive colors, i.e. more such days during a year, but also a much larger geographical extension, an extension that covers essentially many highly vulnerable countries. And you can now start to imagine what the consequence of that is, not only to the individuals who have to cope with that climatic condition over the majority of a year. Red colors mean somewhere between 250 and 300 days by the end of the 21st century of business as usual here. Let's compare this to the Paris targets. 2 degrees warming, global mean. This is a substantial benefit if you compare the two. Substantial benefit. That's the reason why this 2-degree target is a sensible and reasonable target. It will change, people will have to adapt, but the area and the intensity is much smaller, and the adaptability is really given in such a case, or we can work towards it, but in this case, we are reaching the limits of adaptability in many countries, and that is a real issue. Resource water, this is just an impression. That was the cover picture of the special report on extreme events in the last IPCC round. And of course, the water cycle changes significantly with climate change. This is out of the summary for policymakers. It changes regionally. Not all regions are affected by drought. Some regions are affected by drought, and it's interesting to note that it's these regions that already now are challenged by the shortage of water. They will be challenged even more and pushed more towards the boundary of their adaptation capacity. Whereas other locations here in the mid and high latitudes get more precipitation when we don't really want them. So we will have to adapt as well, for example, with the sewage systems and with the electricity system that we all depend on. So the water cycle here changes dramatically for a business as usual. Resource land, I've mentioned, the third resource, loss of home and habitat. That's very clear and undisputable. If sea level rises, you will lose land, and that land loss can be quantified. This was another difficult problem in the last assessment report, to find consensus in the science about the projections of sea level rise. We did find it. This is still an open topic, and I'm looking forward to the projections in the forthcoming assessment report. But given that, we have adapted to 19 centimeters of sea level rise in the 20th century, but compare that to a business as usual requirement of another 70 centimeters. So there are many areas in the coastal zones where hundreds of millions of people live, where adaptation is required. Either technological adaptation, like in the Netherlands, or migratory adaptation, such as, for example, in Bangladesh and other low-lying countries, Pacific Islands, etc. These are huge tasks that lie in front of us. And if you just look at the slope of these curves, the task is not over in the 21st century. It continues well into the 22nd century, because these curves will go higher beyond 2100. The fourth resource, and I could go on, but what I really find important is that you make a connection between climate change, which is something physical, and the question of resources. The fourth resource is biodiversity and the effect of the compound climate change impact. Compound means, for example, temperature and precipitation change, or temperature, precipitation, and land use change, where you have managed land. And so I just quote a recent study here that was published in the Transactions of the Royal Society this year on where are the locations of biodiversity loss exceeding 10% caused by either land use in blue, or climate change in orange, or both in black. And you see here for RCP 2.6, the 2-degree warming, yes, many areas will face a biodiversity loss for various reasons. You see here a rather colored picture, but compare this to the business as usual case here with lots of black and now in particular orange colors that point to the key driver of climate change when it comes to biodiversity loss. So I just want to close with the fourth point here to address also the fact that there are the 17 UN Sustainable Development Goals. We shouldn't forget them when we talk about climate change. And one particular sentence in the synthesis report of the fifth assessment report of IPCC is this one: climate change is a threat to sustainable development. If we are serious about sustainable development, we need to address and mitigate climate change. And I just show you here the 17 goals. They have sub-goals, a total of 169 goals that should be ticked off and fulfilled by 2030. That's the Agenda 2030. Of course, these are ambitions, but it's quite interesting to ask the following question. If we want to achieve some of these sustainable development goals, we can do only if climate change is actually addressed and limited. And here I have just a selection of these few goals that are to be achieved, or cannot be achieved, I should correct myself, cannot be achieved if climate change is unchecked and is unlimited. So, for example, the problem of hunger or the problem of inequalities from countries and regions to regions cannot be addressed if we have ongoing and unlimited climate change. So the climate change needs to be stabilized at a level, the Paris target, to actually be able to achieve these goals. That doesn't mean it's a sufficient condition, but it's a necessary condition. You can turn around that sentence and ask which sustainable development goals need to be achieved to be able to mitigate climate change. And there is, again, here a selection. Obviously, that's a bit subjective. If I asked the audience here to all fill out, we would probably come to slightly different results. But it's clear that we need education, for example. We need also innovation and infrastructure to mitigate climate change. And so you can now compare these two slides with one another and pick out those that light up in both slides, which are these four. And these four, I would argue, are those goals where you have to put your focus on. For example, obviously climate action, decent work, and economic growth. Doesn't mean that the growth is measured in GDP, but there must be new measures of economic growth, in quotes now, responsible consumption and production, peace and justice, and strong institutions. Without these elements, I'm convinced we will not address climate change and climate change mitigation, and vice versa, we will not be able to achieve the sustainable Development Goals. With that, I would like to conclude just as a few take-home messages. The science is clear. We know what's happening, who's responsible, and what options remain. They don't remain forever, as I've shown to you. Some climate targets can be lost, and the climate targets are now precisely defined. For many decades of climate research, as climate researchers, we could not say at what level one should mitigate. We could not say how much carbon dioxide we can still emit. Paris has changed that for us. The policymakers have identified these climate targets, and now we can make quantitative statements about what that means. It's also clear that CO2 emissions must fall rapidly. There's no doubt about that. There are simply no sufficient sinks to compensate the emissions that we have today. And the essential resources are in danger: health, water, land, biodiversity. And I strongly believe in this synergy between the UN Sustainable Development Goals, that ambition, and the ambition to mitigate climate change. So thank you very much, and I look forward to the discussions, questions, and comments you may have. Thank you very much.